Hi guys, today we're going to talk about equilibrium. And equilibrium is another way for balance. You know, it's really important that we have balance in our lives. We like to balance out work, play, sleep. We like to balance out our checkbook. So balance is important in life in general. But today we're going to talk about balance in physics terms. In physics terms, when we have balance, we call it equilibrium. And we're going to focus specifically on mechanical equilibrium, which is when something is stable, when something isn't moving. It's usually called mechanical equilibrium. Let's step back a little bit. Do you remember when you were in like second, third, fourth grade and you were given a definition for force? We said that force was a push or a pull on an object. And what's really important in physics now is that we know that a force is required to change a state of motion. So if you want to make a change, you need to have a force. What do I mean by state of motion? Well, it's either something at rest, so something that's not moving at all, or something that's moving uniformly along a straight line. If it's changing directions, or if it's speeding up or slowing down, it doesn't have a, it has a change in its state of motion. So we want a constant state of motion, and if you want to change that, you need a force. So let's talk about forces. First of all, we have two kinds of forces. We have applied force and net force. And a net force is the combination of all of the forces that are acting on an object. So any force that's acting on an object, you put them together, that gives you the net force. So let's look at a couple of examples. If I had a box and the net force to the right was 5 newtons, and there was another applied force to the right was 5 newtons, and there's another applied force to the right of 10 newtons, we simply add those two together and we get a net force of 15 newtons. Think of it, if you will, like a tug of war. If you're both pulling on the same side, then you add up those, and that tells you what the net force is. Now, if we have something like this where you have 10 newtons pulling to the right and 5 newtons pulling to the left, well, think about it as a tug of war. If you could clone yourself and you had 10 of yourself on one side and 5 of yourself on the other, you're equally powerful, equally rested, absolutely identical. The 10 side would win because the 5 here and 5 here would cancel out, which would leave a net force of 5 newtons. So you can just put those together and you come up with 5 newtons to the right. If we have another box with 5 newtons to the left and 5 newtons to the right, well, those are going to cancel each other out, and the net force is going to be 0 newtons. So I've been throwing around this word newtons. I'd like to talk to you about what the word newtons is. Newton, spelled N-E-W-T-O-N, but abbreviated uppercase N, is just the scientific language for a pound. So if I said, how much do you weigh, you would tell me how many pounds. But in science, we talk about a newton instead of a pound, okay? And there's a relationship between the two. It's not a one-to-one relationship, but we're not worried about that right now. Force, the push or pull on an object, is measured in newtons. So it's measured in that same unit, okay? Newtons. So let's give another example. When you hold a rock in your hand, two things are happening. One is you are literally pushing up on the rock, and the second is gravity is pulling it down, or the earth is pulling on the rock, right? Because if your hand wasn't there, the rock would fall, okay? So two things are happening. If the gravity is the same, is equal as your push up on the rock doesn't move. So if you're just sitting there holding a rock or a book or a pencil or whatever in your hand, the amount of force that you're using to push up is the same amount as the force that the gravity is pulling down, and it doesn't move. It stays right where it is. If, however, gravity is greater than your push, so you're pushing up, but gravity's pulling down greater, if you've ever lifted something really heavy, you know exactly what I'm talking about, the rock will fall towards the ground, okay? So if your push up is less than gravity's pulled down, the rock will fall towards the ground. And likewise, if gravity is less than your push, what happens? Well, the rock moves up and it moves away from the ground. So you might go, whoa, like that, and the rock flies up, right? Because your push has more of a force than gravity. On my previous example, I just showed left and right net forces, but it also works up and down as well. So let's talk about another force. Let's talk about tension. Tension is the stretching force of a spring. I'm sure you've seen this before. If you've ever gone to the grocery store, and now they have those digital balances, but they used to have spring scales. and it looked kind of like this. There was a little circle thing with a dial, kind of looks like a clock, and that moved around, and there was a spring, and then let's say we put on a 2-pound bag of onions on the bottom of that spring scale. Well, this would either show 2 or it might show 9 if you were measuring in scientific units, because remember, pounds and newtons are ways of measuring force. 2 pounds is about 9 newtons, so you might see 9 newtons. So what's happening? Well, the force of gravity, or the earth, is pulling the onions down with a force of 9 newtons, but the spring is pulling up with a force of 9 newtons. How do you know that's the case? Because it's not moving. When it's going like this, up and down, you know, when you very first put it on, it moves up and down. Those forces are unbalanced. But once it stops moving, you can actually read the mass or the weight of the onions, and then it's balanced, okay? So the gravity, F with a little g next to it, that's called F sub g, force due to gravity. And this is force due to the spring, the little F, S says spring, are in equilibrium, they're the same. So the two forces are equal in size. We now have another word for equal in size, it's called magnitude. Magnitude is just the number, it's just how much. But they're opposite directions. And in just a minute, you're gonna see why direction is so, so important in physics. If you have 9 newtons up, that's what the spring is pulling with, and 9 newtons down, that's what gravity is pulling with, the net force is 0 and the onions are at rest. There's no movement because the net force is 0. So force is represented by an arrow, and it's really important to include the tip of the arrow as well as the length of the arrow. It's scaled so that length equals the amount of force. So the longer an arrow has more force, smaller arrow has less force. If you noticed on a screen a couple back, when I had those forces and the little box and I said we're doing the tug of war, the 10 Newton force was twice as big as the 5 Newton force because it's scale, it's to scale, okay? So the length of the arrow tells you the amount of force or the magnitude. Remember that word we just used, magnitude. The arrow represents the direction of the force. Just like I showed you before, if you're pulling with 10 newtons to the left and 5 newtons to the right, there's arrows. Not only is the length of the arrow important, but the direction of the arrow. So make sure you look at what direction that arrow goes. If you have something with magnitude plus direction, that is called a vector quantity. And I know that's a new vocabulary word. You probably want to jot that down. Vector quantity is magnitude or size plus direction, okay? So there's lots of things in physics that are vector quantities. Some are not vector quantities. We're going to talk about that in just a minute. But force is a vector quantity. It requires that you not only tell me how much force, but what direction that force is working in. It could be left, right. It could be up, down. It could be north, south. There's lots of ways to express the direction, but you must express a direction with force. Easiest to do with an arrow. And finally, you have things, you have numbers, you have variables, you have constants that do not have direction. They only have magnitude. They're called scalar, S-C-A-L-A-R. You might want to write that one down also. A scalar quantity has magnitude only, just the size. Direction doesn't matter. So what do I mean by that? Time. You don't say time to the left and time to the right, time up and time down. That doesn't make sense. It's just time. Now, yes, I know we can talk about time in the past and time in the future, but that's not a direction. We're talking specifically about a direction here. Area, the area of a square. We don't say this is the area, it's 32 square centimeters to the left. That doesn't make sense. The area is just 32 square centimeters. Likewise, volume. Something might be 107 cubic centimeters, but we don't say it's 102 cubic centimeters up. We just say cubic centimeters. So the difference between a vector and a vector has magnitude and direction, so size and direction, usually represented by an arrow. Scalars have magnitude only, just a number, not a direction.